This schematic presents an immediate paradox. How do we calculate a definitive value for a circuit that stretches to infinity? Solving these requires looking past the visual layout and applying two rules of current flow. For series combinations, current remains constant while voltages add up. This results in the additive formula shown here. R sub S equals R1 plus R2 plus R3. In parallel combinations, voltage remains constant across branches while the current splits. This gives us the inverse additive formula. 1 over R sub P equals the sum of the reciprocal resistances. Many standard networks, no matter how intimidating, are compounded variations of these two fundamental behaviors. This cluster of three 30-ohm resistors prompts complex parallel calculations, but that's a visual distraction. If we trace the nodes, we see a continuous wire starting at node A on the left, bypassing the resistors entirely, connecting directly to the second node A. Because current takes the path of zero resistance, that complex loop is bypassed entirely. It is functionally invisible to the electrical reality of the circuit. Consider a uniform wire of resistance R bent into an n-sided polygon. We want the resistance between adjacent corners A and B. Resistance divides equally, one R over N segment between the corners and N-1 segments remaining. This redraws as a standard two-branch parallel circuit. Now we apply the parallel formula to these two branches, substituting our values into the equation. 1 over R sub P equals 1 over R1 plus 1 over R2. After simplifying the algebra, we find the final result shown in the bottom left, N-1 over N squared multiplied by R. These geometric problems are effectively mapping exercises, where the goal is to translate physical shapes into standard parallel and series branches. Returning to the infinite ladder, we have a network where every unit is identical. To calculate the total resistance, we define the value between nodes A and B as the variable x. Removing one unit from an infinite chain leaves the rest of the chain unchanged. This allows us to replace the entire infinite tail starting at nodes M and N with that same variable, x. We then build our equation by combining the two 1-ohm series resistors with the parallel block containing x and set the total expression equal to x. This produces a quadratic equation, x squared minus 2x minus 2 equals 0. Applying the quadratic formula leads us to the final value, 1 plus the square root of 3 ohms. Infinite resistive networks are manageable once you identify the repeating unit and substitute the remainder with a single variable. Solving equivalent resistance problems requires two primary tools: grounding complex layouts and basic formulas, and using node tracing to isolate short circuits. We also translate geometric perimeters into branch fractions and use algebraic substitution for repeating, infinite patterns. Mastery comes from using this logical toolkit to reduce any network to its simplest mathematical form.